Hey everyone, here's our math problem for today. This is taken from the Harvard MIT Math Tournament in 2018, and this is problem number 5 for the general round. Here's the problem. Compute for the smallest positive integer n for which the expression the square root of the quantity 100 plus the square root of n plus the square root of the quantity 100 minus the square root of n is an integer. You can pause the video and see if you can solve this Harvard MIT Math Tournament problem. Now let's solve this problem together. Let's take note that we are solving here for the smallest positive integer n, such that when you substitute that n into this expression, the resulting value is also another integer. So, what are the positive integers? These are 1, 2, 3, 4, and so on, or the positive whole numbers. 0 is not included in the solution here. But you will notice later on that 0 will play a crucial role here in identifying the upper bound of our solution. So let's begin first by assigning a variable to the value of this expression, and let's use the variable k. So let k be the value of this given expression, where k is an integer. Since we are dealing here with square root, let's square both sides of this equation. And simplifying, we have here a square of a binomial, which we can simplify by squaring the first term plus twice the product of the first and the second term plus the square of the last term. So this part here is the square of this first term. This part here is the square of the second term. This middle part here is twice the product of the first and the second terms. Now notice that this 100 plus this 100 becomes 200. Then this square root of n minus itself is 0. So we do not need to write the square root of n anymore. And simplifying this middle part here, we copy the 2. And you have here the product of the sum and difference of two numbers, which is equal to the difference of two squares. So the square of 100 is 10,000, and the square of the square root of n is simply n. Both of them are under the square root symbol. Then notice that there is a common factor of 2 here, so let's factor out the common factor 2. 200 divided by 2 is 100. 2 divided by 2 is 1, so we just copy the expression under the radical sign. Now, what does this imply? This implies that k squared is an even integer because that is divisible by 2. And when k squared is an even integer, this also implies that k itself is also another even integer. So let's remember these results. Let's establish the boundaries. We want the smallest positive integer, and 0 is not part of that, but 0 can serve in computing for the boundaries of the value of this expression. That is because if we let n to be equal to 0, then this expression where n is equal to 0 must give us the maximum value of k squared and therefore the maximum value of k. So let's substitute 0 for the value of n, and this resulting expression must be greater than k squared. Because if n is greater than 0, then this expression 10,000 minus that value of n must be slightly lesser than when n is equal to 0. So if n is 0, this expression here must be a little bit higher than the value of k squared that we want to find. So simplifying, this becomes 2 times the quantity 100 plus the square root of 10,000 is 100. So 200 times 2 is 400, or k is plus or minus 20. But since we are after the positive n value here, we just take the positive value, which is 20, and k must be less than 20. Since k is an even integer and k must be less than 20, then the next even integer that is less than 20 must be 18. So when k equals 18, that means the value of this blue expression is 18. That will give us the smallest positive integer value for n that satisfies this problem. So we can now substitute 18 for this k. So here is now the result. Substitute 18 for k. Simplifying, 18 times 18 is 324, copy all the rest. Then divide both sides by 2. We subtract 100 from both sides, and we square both sides to eliminate this radical symbol. 62 squared is 3,844, and we eliminate the square root symbol. Then rearranging to solve for n is equal to 6,156. And this is now the solution to this problem. Notice that we are solving for the smallest positive integer value of n, and that smallest positive value for n happens to be 6,156. Now to check if our solution is correct, let's substitute 6,156 to n, and here is the result. We copy the square root of 100 plus the square root of 6,156, where n is now equal to this result. Do the same substitution for the second term. Now simplifying this, you will discover that the square root of 6,156 is just the same as 18 times the square root of 19. So we replace the square root of 6,156 by 18 times square root of 19, the same thing here. Then splitting this 100 so that one of the numbers is a perfect square, we now have 81 plus 19, which still equal to 100, the same thing here. 81 plus 19 is equal to 100. Now the beauty of this is you have this square root of 19 and you have this 19. Notice that 81 is equal to 9 squared, and 19 can be written as the square root of 19 squared. This form is a perfect square trinomial because the middle term is equal to twice the product of this 9 and this square root of 19. The first and the last terms are both squared. So we can now write this expression as the square of the binomial 9 plus square root of 19. Here, it's also a square of a binomial, but the sign is minus. Then simplifying further, notice now that this square root and this exponent will cancel each other out. The same thing here. And so we have 9 plus square root of 19. The other part is 9 minus square root of 19. Then plus square root of 19 minus square root of 19 is equal to 0. And so 9 plus 9 is equal to 18, which is exactly this k value when we have the smallest positive integer value for n. And so it's now confirmed that n is 6,156. So this Harvard MIT math problem is really not that easy to solve. So thank you very much, and we hope to see you again in our next video. Bye for now.